Okay, this video is going to cover examples on Lesson 3 on conditional probability. Again, you can pause the video after you look at a problem, try it for yourself, and then unpause it and see if your solution matches mine. Problem number 1, it says, a jar holds 10 white, 6 red, and 4 blue marbles. If 2 marbles are chosen, what's the probability that the second marble will be red if the first marble is red, and A, if the marbles are chosen with replacement, and B, if the marbles are chosen without replacement. Okay, so part A is asking us to find the probability that the second marble is red given that the first marble is red. Okay, and that means that we're going to make a fraction because we're talking about a conditional probability. Remember that the denominator of the fraction is going to be determined by either putting a probability or a count of the number of ways we can have the sample space to choose out of for the second part, but which meets the condition, right? So we're talking about the first marble is red. All right, so what would be the state of the bag if we're choosing with replacement, okay, with replacement, and we're getting ready to choose the second marble, but the first marble was red? Well, if we replace the marble in the bag, then that means after the first marble is chosen, what will be in the bag? We'll have 10 whites, 6 reds, and we'll have 4 blue marbles because we replaced whatever marble we got back in there, and we have all the marbles. Okay. And it says that the first marble was red. So, so that means that there are still 6 plus 4 is 10 plus 10 is 20. There are 20 marbles in the bag to choose from, right? And we're talking about finding the probability now that the second one is red. So the numerator of the fraction is going to come from meeting the event, the criteria to be the event. That is that the second one is red. So out of the 20 marbles, the conditional sample space of the bag after the first marble has been chosen, and in this case replaced, what's the probability that we would get a red marble? Well, that will be 6. There are 6 possible ways to get a red marble. So 6 out of the 20, and that means we would have a probability of, turns out to be 0.30. So if you put that in a calculator, 6 divided by 20 is 0.3. So there's a 30% chance of getting a second red marble if the first marble is red if you replace the marble. Okay, so let's do part B. Part B, same thing. We're finding the probability that the second marble is red given that the first one was red. Okay, and we have something for the denominator. That's going to be the number of ways. It's going to define what the sample space is, the conditional sample space. So if we drew a first red marble out, but this time we're not replacing it, then that means after the first marble is drawn out, right, it says specifically a red marble is drawn first, right? So that means we still have all 10 whites in there, but now there's only 5 red marbles, and then there's 4 blue marbles, right? So that means there are actually 19 marbles left in the bag because we're not replacing this time. And then for the numerator, we're going to talk about the probability that we get a red marble the second time. So out of this conditional sample space here, right, the probability of getting the 5, the number of ways to get a red is 5. So there are 5 red marbles now out of the 19. And that means that the probability is 5/19, which turns out to be 0.2632. Okay, right, a lower probability because we took out a red marble the first time, and that lowers the overall number of red marbles in the conditional sample space bag there. All right, so did you get the answer right? Let's go ahead and go to the next problem. We can read it, pause it, and then try it, and then unpause and see if you got the right answer. So this one says a sample of 100 people at a mall were asked to try 2 different soft drinks and state their preference. The results are shown in the table. So we have drink A and drink B, and we have different totals for males and females. A, let's just do these one at a time. What's the probability that a person selected at random from this group will drink A? Okay, so the probability that a person will drink A, let me just write the probability statement for that. It says we're finding the probability that a person selected from the group will drink A, right? So all we're finding is the probability that a person drinks A. There's no conditions or anything like that. This is what we would call a simple probability. It means that we're going to use the entire table to figure that out. Now, since we have a table here, we probably should go ahead and find what are called the marginal counts. So the total number of people that drink A is 44. And if I add up 38 and 18, that turns out to be 56. So there's a total of 100 people here. And 22 plus 38, looks like 60 of them were males and 40 of them were females. Okay, so what that means is the probability of drink A, since this is just a simple probability, it means out of all 100 people, how many liked drink A? Well, drink A's column total is 44, so it would be 44 out of 100, or 0.44. So one of the important things here is distinguish conditional probabilities from simple probabilities. There's nothing here that gives a condition. It's just out of the entire group of people, one person selected at random will prefer drink A. Okay, let's do B. So this one is asking us, what's the probability a person selected at random will be female? So again, this is from the entire population probability of being a female. And that means out of all 100 people, what's the probability of being a female? So female is 40 of them were female, so 40 out of 100 is a probability of 0.40. So that's also what we call a simple probability, because we're sampling out of the entire sample space. Part C says, what's the probability that a person selected at random is a male and prefers drink B? Now, this might seem like something more complicated because of this word and. But male and preferred drink B is just a specific place in the tree. Male and preferring drink B is this 38 people, right? But it doesn't give any sort of condition here. It just says a person selected at random, presumably from the entire table. So the way I would write this is the person has to be male and they have to like drink B. But again, it's out of all 100 people, how many people are male and like drink B? That's 38. So that would be 0.38. 38% chance that a person selected at random would be male and like drink B. What's the probability that a male from this group will prefer drink B? Now the structure of this sentence is different. It didn't say a person selected at random, it said a male from this group. Now that's a condition. And we're still finding though the probability that the person will drink B. So this male from the group is really the kind of parenthetical comment. That makes that the condition, and we're finding the probability of drinking B. So this is sometimes the trickiest thing, getting the statement right. This is the probability that somebody will like drink B given that they are a male. So this one is a conditional probability, and that means that the bottom of the fraction has to come from just the males. So if we look at the males, that means we're restricting ourselves only to the male column. So that means only out of the 60 males, it would be the people that are males who'd like B, which would be 38. So this time it would be that 38 only out of the males, 38 out of 60, which turns out to be 0.6333. So that one's a conditional probability, and it's sometimes hard to get that from the wording. Okay, let's look at the last one here. It says, what's the probability that a person who likes drink B is a male? If I were to put this in parentheses, it would still make sense. What's the probability that a person is a male? That's what we're finding the probability of. Probability that the person is a male, given that they like drink B. So in that case, we're talking about restricting ourselves to the B column, and that means out of the 56 people who like B, how many of those were male? That would be 38 again. But this time it's 38 out of the 56, and so that would be 0.6786. So a good example to illustrate how you have to be careful about what is the denominator and how tricky that it can be from the wording in the statement. Okay, let's move on to another one. It says, if two cards are drawn from a standard deck of 52 cards without replacement, what is the probability that the second card is a jack if the first card is not a jack? Okay, So let's see, the original deck, let's look at it. It looks like everything has to do with being jacks here. So what do we have in the original deck? I'm just going to try to kind of thinking out loud here. The original deck has 4 jacks in it, right? The jack of hearts, jack of diamonds, jack of clubs, jack of spades. And then there are 52 minus 4, there are 48 other cards. 48 cards that are not jacks. Okay. So it says, what's the probability that the second card is a jack, given that the first card is not a jack? Okay. All right, so if the original deck was 4 jacks and 48 other cards, and we drew 2 cards without replacement, okay, which means the second card is drawn after the first card has been removed, then what happens after the first draw, right? After the first draw, which is not a jack, then that means the deck will still have the 4 jacks in it, and it'll have 47 other cards in it now. So now it has a total of 51 cards, right? So I think that means that the probability that we get a second jack given the first was not a jack is, well, the condition of the deck has 51 cards to draw out of at this point, right? And how many of those are jacks? All 4 of them are still in the deck. So it would be 4, right? First card is not a jack. Yeah, it would be 4 out of the 51 cards. Let's do that in a calculator real quick and make sure what that is in decimal. 4 out of 51. 4 out of 51 turns out to be 0.0784. That right? Yeah, so if you got 0.0784 or 4 out of 51, that was correct. Remember, you have to take into account the idea that the one card was removed, and it's not finding anything about like the probability of any specific thing related to the first card. It's just that the first card affects this 51 number, the denominator number. All right, let's move on to the next one. Okay, it says in a particular city, 20% of families have no children, 22% have 1 child, 38% have 2 children, and 12% have 3 children. What's the probability of a family having more than 3 children, and what's the probability that a family has more than 2 children if it's known that it has at least 1 child? Okay, maybe we could make again a picture here to show this, maybe like a table. Let's have number of children and the probability of that. Okay, so you could have no children, 1 child, 2 children, 3 children, or 4 or more children. Okay, so it says the probability, let's see, 20% of families have no children, so I'm going to write that as decimal 0.20. 22% have 1 child, 38% have 2 children, 12% have 3 children, and then what it's asking in part A is what's the probability of a family having more than 3 children? So we're trying to find this probability. Well, we know that if we just lump all of that into one category, 4 or more than 3, then that means that all of these have to add up to 100%. So all I really have to do is add these numbers up and subtract that from 1 to get what's left. And when you do that, you get that there is 8%. So for part A, the probability of having more than three children is 0.08%, just from adding up the other categories and subtracting that from 100%. Okay, then it says we want to find the probability that a family has more than 2 children if it's known that it has at least 1 child. So that is a conditional probability. We want to find the probability that we have more than 2 children given that we have at least 1. More than 2 given that we have at least 1. Okay, so the at least 1 part is going to form the denominator down here. And we can use either counts or probabilities. So let's go to our table here, which is really a sample space listing, and look at all the cases which are at least 1. So at least 1 is all of this, all of those cases there. So out of, let's see, that's going to add up to, well, if this is 20%, that's going to add up to 80%. So 0.22 plus 0.38 plus 0.12 plus 0.08. So out of the 80% of families that have at least one child, then what's the probability that we have more than 2 children? So the more than 2 children part would be not the 1, not the 2. More than 2 would be these two cases. So 0.12 plus 0.08, right, which would be 0.2, right? So 0.2 divided by 0.8 turns out to be 0.25. So that's a conditional probability, and we have to figure out what represents the conditional probability. You can use either counts, or you can use percentages, or you can use decimals for probability like we did here. All right, let's go ahead and move on. Okay, so it says the table below shows the political party registration by gender of all 500 registered voters in Franklin Township. Given that a randomly selected voter is male, what's the probability that he's registered for party Y? All right, so one thing about tables like this, sometimes they give you the margin values, the totals, and sometimes they don't. So it's important to recognize this right here is the actual data, and the stuff on the edges are just the sums of the columns and the rows. All right, so it says, what is the probability that the voter is male? Oh, given that the selected voter is male. So that's the condition. Given that they're male, what's the probability that they registered for party Y? Okay, so I think all we need to do then is to say male constitutes the condition. So this is the conditional sample space, a total of 200 males. Out of that, how many were Y? And that would be 48. So 48 out of 200, right? And that turns out to be 0.24. Okay. So again, just because there's a big table and some wording, that doesn't mean the problem's necessarily bad. In fact, tables are very nice because you can see all combinations of things very quickly. It's a very compact and efficient way to convey a lot of information. Okay, let's look at this one. A shopping mall has 3 automated teller machines. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day. The table shows the probability distribution of x. So there's a 15% chance that none of the ATMs are working, 21% chance 1, and 40% chance 2, and so on. Okay, what's the probability that at least one ATM is working? Okay, so for part A, at least one ATM would constitute the 1 case, the 2 case, and the 3 cases. So although we haven't formally been shown we could just add those up, right? It turns out that if there's a 21% chance of 1 and a 40% chance that 2 and a 24% chance of 3, the probability that we have 1 or more is simply the addition 21%, 40%, and 24%, which turns out to be, let's see, that is 85%, right? Yeah, 85%. Technically, we haven't learned that yet until the next video, but I think it's obvious in this case that we're going to add those probabilities. More importantly, though, is this question here. What's the probability that all 3 ATMs are working given that at least 1 is working? That's definitely a conditional probability. We want the probability that 3 work given that at least 1 works. Okay, so the at least 1 part is going to form the denominator, and that is the probability we just found. There's an 85% chance case that at least 1 works. So this becomes the conditional sample space, and then the probability that 3 are working is one specific part of that, the 0.24. So it's just going to be 0.24 divided by 0.85, which means the probability is 0.2824. So the first one was a simple probability, but we had to add multiple cases to form it, and the second one is a conditional probability. Okay, let's move on to the next one. Okay, it says, given the following tree diagram showing probabilities of defective engines from 3 different engine manufacturing plants in 3 cities. So we have Detroit, Spring Hill, and San Antonio, and they each have a different probability of having a defective engine. Okay, and this is already represented as a tree diagram for us. It says, what's the probability that an engine is defective if it came from the Spring Hall plant? So that is a conditional probability, right? The probability that the engine is defective given that it came from Spring Hall. I really like to write out the probability statement like this because that helps me really quickly see what's the numerator, what's the denominator, right? So we're talking about the Spring Hall plant. Well, that means out of all this stuff here in the tree, coming from the Spring Hall plant is basically being restricted to that portion of the tree. So that portion of the tree is the conditional sample space. Right? And then we're finding the probability that we have a defective engine. That would simply be this probability right here. So that one is right on the tree itself. That is a conditional sample space. The probability that defective occurs given that Spring Hill has occurred. All right, let's look at the second one. This one says, I'll use a different color. It says, what's the probability that an engine is not defective if it came from the Detroit plant? Okay, so again, coming from Detroit is the condition, so we'll go to this portion of the tree, and we want the probability of not being defective. That would be this right here, so that would be 0.98. There's a 98% chance an engine is not defective if it comes from the Detroit plant. Okay, then it says, what's the probability that an engine came from the San Antonio plant? Okay, so that one is not a conditional probability. It's just the probability that it came from San Antonio. There's nothing about defects here. So that is, if you want to think of it, it's from the whole tree. It's a simple probability, and we want the probability that we took the path towards San Antonio, and that would be 0.3. 30% chance that the engine came from San Antonio. All right, so that's that one. And just one more to go. Okay, the last problem here, it says 2 events G and H occur with the probabilities shown in the Venn diagram. Find the following probabilities. Okay, so for part A, it says probability of G. That's a simple probability. So it means out of the entire sample space, it means out of the entire universe here, what's the probability that we are in G? Okay, so it's going to be that portion. So it looks like we have to add the 0.3 and the 0.2. There's a total of 0.5 probability in that region. And again, we haven't really talked about the adding. We'll talk about that in a little bit more detail but in the next video, but we can go ahead and see the idea of it now. Okay, for the second one here, B, it says find the probability of H given that G has happened. So on the Venn diagram, the conditional sample space is going to be defined by G. So we have to stay within the G circle, right? And then we're talking only about the things that are H, but we have to stay constrained to the G circle. So the part that's H is this part, this 0.2. So it would be, well, the bottom of the fraction has to be some representation of the G, and the G isn't the entire region, right? So G is 0.3 plus 0.2. In other words, there's 0.5 in G, right? But the H part of that is 0.2. So it'd be 0.2 divided by 0.5, which turns out to be 0.4. So if you are in the G circle, there's a 40% chance that you'll be in the H circle as well. Okay. We'll explore conditional probabilities a lot more in lesson 6, where we can combine or and case formulas. There's other formulas for this too. But what I'm trying to get us to see right now is the connection with that conditional probabilities have with a portion of the sample space. Okay, part C here says the probability of G given that H has happened. So in this case, H is the conditional sample space, and that means we have to stay within H, which has 0.2 plus 0.4 or 0.6. there's a 60% chance of being in H. Now, if you're in H, what's the probability that you are in G? So the G portion of that is the 0.2. So this time it'll be 0.2 over 0.6, which turns out to be 0.3333. So it matters very much what direction things are going. Okay, and the last one here, it says, what's the probability that G occurs given that H does not occur? That line over the H means the complement, or everything other than H. Okay, so that means a conditional probability again, and this has to represent all the things that are not H. So what I'm going to do is I'm going to draw a circle around H, but it's really everything outside of the H. This is the conditional sample space, which consists of that 0.3 there, plus this 0.1. So there's 0.3, and there's a 0.1. There's a total of 40% chance that you're not in H. And if you're not in H, what's the probability that you're in G? So the portion of this not H part that's in G is this part right here, and that would be 0.3. So it's going to be 0.3 out of 0.4, which turns out to be 0.75. Okay, so the main thing I wanted you to get from these examples is if you can find a way to list the sample space, either physically or numerically, with diagrams, trees, Venn diagrams, or whatever, the numerator is, well, the denominator first is the portion that is the condition, and then the numerator is the part that meets the event within the conditional sample space. Okay, that's all I have for examples at this time. But again, we'll talk about conditional probabilities more after we've covered the AND and OR rules in the next videos.